Hello everyone. In this lesson we're going to expand on our tool set of ways that we have to solve quadratic equations. So far we really only have two. You can solve by factoring. That's for equations that are factorable. And then in the last lesson we learned about taking square roots. And so we're going to start by just reviewing how that taking a square root one went. And that's what these two examples are meant to do. So if you would please pause the video now and try these as kind of warm-up questions to lead us in and to jumpstart our discussion for what we're going to be looking at today. So the steps that we talked about in the last lesson were to get the squared item by itself, use the square root to undo the square, and then solve for your two solutions. Most of the time you get two solutions. So pause the video now, unpause it once you've had a chance to try and want to see what the answers are. Okay, welcome back. Let's talk about the two. The first one works out like this. You divide by 4 to get the squared item by itself, then you take a square root. The square root of 9 is plus or minus 3. And that square root cancels the square. You're left with x plus 1 on the left-hand side. That means that x plus 1 is either equal to a positive 3 or x plus 1 is equal to a negative 3. Subtracting 1, you get 2. Subtracting 1, you get negative 4. Let's check. Put 2 back in. 2 plus 1 is 3. 3 squared is 9. 9 times 4 makes 36. It works. The second one you might have had an issue with. If you get the squared item by itself, you subtract 6x, you're trying to take a square root, there's nothing to do, you get stuck. So I chose this second one to kind of justify what we're going to be doing. We need a new tool. If you look at the last lesson, every single quadratic equation that we were solving, none of them had an x term in it. If they have an x term in it, we're going to need to manipulate the equation so that we can take a square root. So the second example was to justify, to show, to illuminate for you that we need a new tool. And that new tool that we're going to get today is called completing the square. In order to really see where it comes from, we're going to go back and we're going to look at some special cases where we had perfect squared statements, and we're going to look at what was going on. How could I put an expression back together to make a perfect square statement? So let's review, how do we multiply these types of things? You cannot just distribute the square. It does not just make x squared plus 9. You have to multiply it out by doing x plus 3 times x plus 3. Then you do multiple distribution. X times x makes x squared. X times 3 makes 3x. Then you distribute the 3, you get another 3x. Look, they double in the middle. 3 times 3 makes 9. So your final answer statement would be x squared plus 6x plus 9. What I want you to notice is this. Look, the 9 is going to be the 3 times the 3, and the 6 is double it. So the 6 is 2 3x's. I hope you can kind of pick out what the rest would be, just picking out this pattern. This 3 got doubled to make the 6x in the middle, and it multiplies by itself. It squares itself to get the last term. If it was x minus 4 squared, what's going to happen? You'll double the middle term, you get minus 8x, and then you square to get 16. Essentially, the negative 4 is half of the middle term, and then the 16, the last term, is the square of that half of negative 8 being negative 4. With 7, what's going to happen? Well, in the middle, there'll be 2 7s, so that'll make 14 x's, and at the end, there's going to be a 49, because it would multiply 7 times 7. Just trying to pick out the shortcuts that are going on. If you need to go back and do it the longer way by writing it all out, that's fine. But we're going to need this shortcut because we're going to eventually work backwards. We're going to kind of have a statement like this, and then we kind of need to work backward toward the left. So we're going the forward case so you can see what the pattern is. This last one, there's minus 5, so 2 minus 5's in the middle will be minus 10x, and then minus 5 and make a plus 25 at the end. So hold on to this idea. We're going to need it here in a moment because we're going to go backward. Here's the idea, and this is kind of a very, very old idea. This actually idea is like thousands of years old. What we're trying to do is we're trying to take a statement like x squared plus 8x, and here realize we have an x term, and so that's why we're looking at ones like this, because I want to eventually be able to take a square root, but I can't right now because that x term would get stuck like we saw in the warm-up one. If I subtract 6x, 40 minus 6x, I can't make that be anything. Those aren't like terms, so when I take their square root, I can't do anything. So what we're trying to do is this. We're trying to make a perfect square, because if I have a perfect square, I can take square roots of perfect squares. And thousands of years ago, they didn't have algebra, but they used geometric interpretations. They used little pictures and tiles in order to understand what they were doing. So this picture down below is a little closer to how civilizations first thought about this. Here they have an x squared and then 8 little rectangular x's. Right now that shape makes a rectangle, clearly. but I want to move the pieces around to start to get closer to a square. So this is what they would do. They would say, okay, let's take one of these maybe. If I put one of them down here, I'm starting to get closer to a square, but now it's 1 by 7. Let's go with 2. Now it'd be 2 by 6. I'm getting closer, but I need a square, and a square has equal sides. If this is 8, each of the sides needs to be half of 8, 4 by 4. So what they would do is they would take half of whatever the x term was, and they would move them along the sides. And now they'd say, oh, okay, look, my sides are 4 by 4, and that is much closer to a square, but they realize there's a gap missing here. I'm going to grid it out, kind of like a Hershey's bar or something. If I grid it out, you see how many little 1 pieces I'm missing that I need to fill in order to make my perfect square. I'm missing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I don't want to count those out every time. What happened? Well, when I took this and cut it in half and made 4 by 4, 4 times 4 is going to make 16. I need to add 16 in order to make a perfect square. And now I can factor it. What two numbers multiply to make 16 and add up to be 8? 4 and 4. So this is x plus 4 times x plus 4. But what's a better way of writing x plus 4 times x plus 4? We would write it as x plus 4 squared. And that's where the term squaring really kind of came from algebraically. You can see this is x plus 4 by x plus 4. It describes the shape that you're making. So if I were able to add 16, I would have a perfect square. It'd be x plus 4 by x plus 4. Let's try it with this one. If I have x squared plus 2x, it currently makes a rectangle. I need to take half of 2, which is just 1. Move it down here. Now I have equal sides. I still am always going to have a gap I have to fill in. What do I need to add? I need to add 1 by 1. I need to add 1. I need to add 1 right here in order to make a perfect square. If I add 1, I can factor this. What two numbers multiply to be 1 and add up to be 2? Well, 1 and 1. X plus 1 times x plus 1, we write as x plus 1 squared. We call this process completing the square. It's called completing the square because the first types of ways that we did it, it was a geometric interpretation, and you are making a perfect square. You are making squares. Algebraically, you're making perfect square statements, expressions. We're going to practice it with a few. If you need to, you don't have tiles, you can just draw a little box to show what's going on. So imagine I have x squared plus 6x. If I was using the box, it'd look like this. I have x squared plus 6x's. Right now I have a rectangle. I'm not even using these parts down here. So what do? We have to take those 6x's and I have to split them so that they're equal on the sides. Half of 6 would be 3 and 3. So the process is always cut that in half. If it's 3 by 3, I have a gap down here to what do I need to add? 3 times 3 makes 9. So this, I need to add 9. If I were able to add 9, it would make a perfect square. I can factor it now. What two numbers multiply to be 9 and add up to be 6? Well, x plus 3 and x plus 3, 3 and 3, so this would be x plus 3 squared. Watch. Your multiplication table would look like this. X plus 3 and x plus 3. X times x, x squared. X times 3, 3x. X times 3, 3x. 3 times 3, 9. Next one. The bigger eraser. There we go. X squared minus 10x. We have a negative this time. X squared minus 10x. This is what my picture looks like right now. It's a rectangle. And so what would we do? We would say, okay, I need to make a square. Let's take half of those minus 10s. That would be 5 and 5. So negative 5x, because they still are negative. And negative 5. I haven't really done anything besides move the pieces. Now I see my gap right here is negative 5 times negative 5. That's going to be 25. Notice this number down here is always going to be positive because it's either a negative times a negative or a positive times a positive. I need to add 25. Then I would have a perfect square. I can factor this. What two numbers multiply to be a positive 25 and add up to be a negative 10? It would be minus 5 and minus 5. So the factors on each side are x minus 5 squared. This is x minus 5 by x minus 5. We call this process completing the square. It's what's going to allow us to solve equations when square roots wouldn't have allowed us to. I'm going to ask you to try. So pause the video now and then unpause it once you've had a chance to try these two. Tell me what you would need to add in order to make a perfect square, and then tell me what that factoring would be. What would the actual dimensions of the square be? So pause the video now. Come back after you've had a chance to try. Okay, welcome back. What you should have got is you'd split negative 14 to be negative 7 and negative 7. That would multiply to be 49. You need to add 49 in order to make it a perfect square. Its dimensions would be x minus 7 by x minus 7. That'd be x minus 7 squared. Over here, if this is negative 20, you need to split it to be negative 10 and negative 10. Negative 10 times negative 10 is 100, so you need to add 100. Now it's factorable, and it's going to be x minus 10 by x minus 10, so we'd say x minus 10 squared. You would have a perfect square. That's the first half of the lesson. That's kind of me showing you how the tool works. Now we're going to actually start to use it. So here, we're going to use it now to solve an equation. If we had tried to use the tool prior of square roots, let's just remind ourselves why square roots wouldn't work. If I was trying to solve using square roots, I would get the squared item by itself first, so don't write this down because this isn't going to work. I would subtract 6x, and then I try to take a square root, but realize 7 minus 6x, those aren't like terms. They can't talk to each other. Some people think this makes 1x. No, 7 ones minus 6x's, those are not like terms. They will not simplify, and I can't just take its square root. So the 6x gets stuck. I have to manipulate the equation to make a perfect square so that I can take a square root. Here's what the picture looks like right here. So the picture looks like this. What would we do? We would need to move those 6x's. We need to take 3 of them. And I'm going to, did I get 3? Maybe I got 4. Let's see. No, I got 3. We're going to rotate them, and then we're going to move them down here. So I haven't really done anything yet besides just moving some pieces around. So I'm showing what the picture looks like because some people really appreciate the picture. Now I see my gap. My gap is 3 by 3. I need to add, so let's draw I'm getting closer to a perfect square. I can kind of see it right here. There's the outline of it. I need to add 9 here. If I gridded it out, it'd be a 3 by 3 grid. I need to add 9 in order to make a perfect square. But if I add 9 to the left-hand side, I need to add 9 to the right-hand side as well. So I need to add 9 to each side. I'm going to do it because the left-hand side is going to be factorable here in a moment. I get x squared plus 6x plus 9 equals 7 plus 9 will make 16 on the right-hand side. Now the left-hand side is factorable though. What numbers multiply to be 9 and add up to be 6? 3 and 3. It's what we were just practicing a second ago. So this left-hand side can be rewritten as x plus 3 times x plus 3. It can be written as x plus 3 squared. And now look at the beauty of that. I can take a square root and nothing will get stuck. We've manipulated the equation in a very clever way so that I can use a square root. It's a very, very brilliant idea. It's one of the most famous mathematical ideas for Algebra 1. Now that I have a perfect square, I take the square root, and the square root will cancel the square, and I'm going to get 2 answers. This is kind of like the warm-up one that we did. Either x plus 3 will equal negative 4, or x plus 3 will equal positive 4. I solve for my 2 answers because it is a quadratic at the end of the day. There should be expected to be at most 2 answers. So negative 7, subtract 3 and 1. Let's check. Let's check with 1. Put 1 back in the equation. 1 squared is 1 plus 6 times 1. 1 plus 6 makes 7. Negative 7 will work as well. You'll end up getting 49 minus 42. And that is the process of completing the square to solve a formula that you couldn't prior. A very, very, very clever and famous idea. Let's try one more, then I believe I'll have you try one, and that'll be it. So let's try this one. X squared minus 8x equals 5. If I tried to solve using square roots and added the 8x over and then took a square root, all things would get stuck. It would come to a screeching halt. So I need to manipulate the equation to get a perfect square. I'm going to use the picture to help me. Instead of placing all minus 8x's here, I've already split it to be minus 4x and minus 4x. Now I can see what I need to add to each side. I need to add a 16. I need to add a 16 here because it'll make a perfect square. And if I add it to the left, I also need to add it to the right side of the equation to keep the books balanced, like balancing a checkbook. So that's what the picture looks like to help justify to me what I'm going to do. Over here, I'm just showing I added 16 to each side. So I have x squared minus 8x plus 16 equals 5 plus 16 is 21. Number one mistake I see people make is they always know that they need to add 16 to the left because they're trying to make a perfect square, but almost always the number one mistake I see people make is they forget to add 16 to the right to keep it balanced, or whatever number they're using to balance. It's not always 16. Now this is factorable. What 2 numbers multiply to be positive 16 and add up to be negative 8? Well, it's going to be what my picture shows, x minus 4 and x minus 4. So that would be x minus 4 squared equals 21. Now I have a perfect square and I can take a square root and nothing will get stuck. Square root, square root. Unfortunately, 21 is not a perfect square, so I'm going to have to use decimals to approximate. Square root of 21 Let's go to 2 decimal places, 4.58. There'll be 2 answers, so it'll be negative 4.58 and positive 4.58. So x minus 4 equals negative 4.58, or x minus 4 equals positive 4.58. Solve by adding 4, I get negative 0.58. Solve by adding 4, 8.58. And you can always, and probably should always, check by plugging your values back in. If you put 8.58 in for x and square and then subtract 8 times that value, you should equal 5, approximately. We did round, so it'll be just slightly off. There we go. There's the last one that I'm fully presenting out with talking example. I'm going to ask you to try this last one before I go through it quickly. So pause the video now, see how you do in using completing the square to solve a quadratic for yourself. So pause the video now, please. Okay, welcome back. Let's see how it went. I'm going to go through it kind of quickly. If you had 4x's, you'd want to split it to be 2x and 2x. 2x and 2x shows us that we need to add 4 to each side. 4 because it'll make a perfect square here, and then 4 to the right-hand side to keep it balanced. So it'll look like this. When I add 4 to this side, I'll get 9. Now this is x plus 2 by x plus 2. We'd say that's x plus 2 squared equals 9. Now I have a perfect square. I can take a square root. Square root, square root. You're going to get 2 answers. Either x plus 2 is negative 3 or x plus 2 is positive 3. Subtract 2, you get negative 5, negative 5. Subtract 2, positive 1, positive 1. Here's your 2 answers. Thank you very much, and have a good one.